One other tool, and again a common tool, very commonly used, but to use a torch and to see how the material reacts to the application of direct heat. Some materials you'll find when we apply heat, the heat will stay very focal to right where the heat is applied, and it stays very focused. Yet others, when we apply heat, it absorbs that heat quickly. So the difference in thermal conductivity of that material can be very important to understand exactly what it is. So it becomes, look at the way it reacts to heat. Does that heat stay very centralized and focused, or does it run away? What colors do we find around where we apply the heat? Do we find it just stay cherry red when that heat's located or directly where it's supposed to be? Or do we find more of a rainbow effect? And you can see where we've ran this test multiple times. Unlike this titanium, you see that rainbow effect around where the heat is applied. And you'll find that same effect true between the titanium and the stainless steel. But we will, again, run this test. Again, a common tool, but it is very important to see how it reacts to that correct heat. Okay, with the titanium, you'll find the heat to be very focused, and the way it absorbs that heat, it'll stay fairly centralized to where we apply that heat. It doesn't just absorb it and spread it out uniformly. And you'll see we'll get that cherry red color, much like we see with the carbon steel, but it's what we find after we remove the heat. We'll find that rainbow pattern along the heat line. Our cold rolled steel, when we apply the heat, you'll find with cold rolled, just like hot rolled, you'll find that the heat will stay very focused where we apply the heat. It doesn't spread out. It does stay fairly centralized where we apply that heat. We find it go to that cherry red color, but we don't necessarily see that rainbow pattern like we did with the titanium or like we'll see with the stainless steel. Again, a piece of hot rolled, a little thicker piece, so it's taking a little longer to heat. But again, the heat stays fairly focused to where I apply that heat. It's not running and being absorbed throughout the plate. And again, we find that directly there. Piece of stainless steel, we find to be very much like, again, the titanium. We'll find go cherry red directly under the heat source. The heat stays fairly focused to where it's applied. And again, we find that rainbowing pattern around where the heat was applied. Okay? So the flame test is very important. Now, as crazy as it sounds, how does aluminum react to a direct flame? Aluminum is much different. Aluminum being very different. Aluminum will not change color. Aluminum absorbs heat. Why we find many times the frying pan that you use at home in your kitchen is made of aluminum because of the way it absorbs heat. Very uniform. It's got a high thermal conductivity. As I apply heat on this location, I find it gets very hot. to the complete opposite side of that plate as it's absorbing that heat quickly. So with aluminum, you will see no change in color. You won't see anything take place other than it will change state. It will go from being solid to liquid. And that's the only thing you're going to see as you heat up that material. Now, as you'll learn in our last section of this class, there are a lot of unique characteristics with aluminum. There are many unique characteristics with aluminum. Aluminum naturally forms on its surface aluminum oxide. Aluminum oxide has 3 times the melting point of the base metal. So what happens, and especially here you can see, the aluminum oxide, which is much harder than the base metal itself, actually acts as a form and holds the metal in place. So as we were heating the surface, that heat being transferred through, the inside of that material, the innermost part, reached its boiling point, its melting point. It was melted. But the outside, with that aluminum oxide being a much higher melting point, actually kind of held it together. So, but again, raw aluminum without the oxides, we're talking 1200 degrees melting point. But yet when we go with aluminum oxide, we're talking about 3700. So as you can imagine, to weld aluminum, very, very important. The oxides need to be removed if we want to ensure that the weld penetrates properly. So very, very important. But the flame test, again, is another means, a simple tool that most facilities have in their possession that you can easily check and help to distinguish between your different materials. And again, how it reacts to a direct flame and what you see of the color and where that heat, whether it stays fairly centralized to where it's applied, whether it's absorbed, and again, the coloring left after we take that heat away.